Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. All right, you are in for a major treat this time. Last week, I had a chance to stop by the Googleplex in Mountain View and sit down with none other than Jeff Dean, Google Senior Fellow and head of the company's deep learning research team, Google Brain. As you'll hear, I was very excited for this interview because so many of Jeff's contributions since he started at Google in 1999 have touched my life and work. In our conversation, Jeff and I dig into a bunch of the core machine learning innovations we've seen from Google. Of course, we discuss TensorFlow and its origins and evolutions at the company. We also explore AI acceleration hardware, including the TPU, versions 1 and 2, and future directions from Google and the broader market in this area. We talk through the machine learning toolchain, including some of the things that Googlers might take for granted, and where the recently announced Cloud AutoML fits in. And we discuss Google's process for mapping problems across a variety of domains to deep learning, and much, much more. This was definitely one of my favorite conversations, and I'm pumped to be able to share it with you. Before we jump into the show, though, a few quick questions for you. Are you an IT technology or business leader who needs to get smart on the broad spectrum of machine learning and AI opportunities in the enterprise? Or perhaps someone in your organization could benefit from a level up in this area, or maybe you could benefit from them leveling up. If this sounds like you or someone you know, you'll probably be interested in my upcoming AI Summit event. Think of the event as a 2-day no-fluff technology plus strategy MBA in machine learning and AI. You'll leave with a clear understanding of how machine learning and deep learning work, no math required, how to identify machine learning and deep learning opportunities within your organization, how to understand and take advantage of technologies like computer vision and natural language processing, how to manage and label data for ML and AI, and how to build an AI-first culture and operationalize AI in your business. You'll have an informed perspective of what's going on across the machine learning and AI landscape, and we'll be able to engage confidently in discussions about machine learning and AI with your colleagues, customers, and partners. I'm very excited about this event and the expert speakers you'll get a chance to learn from. For more information, visit twimlai.com/AI Summit and feel free to contact me with your questions. You can reach me at Sam Charrington on Twitter or shoot me an email via twimlai.com/contact. We hope to see you there. And now, on to the show. All right, everyone. I am here with Jeff Dean. Jeff is a Google Senior Fellow and head of Google Brain. Welcome to This Week in Machine Learning and AI, Jeff.
Thanks for having me.
I've got to say, I am quite starstruck to be sitting here on the Google campus with you. I was at the Scaled Machine Learning Conference Saturday where you had a chance to speak, and I didn't realize this until Reza mentioned it in your intro, but there's a whole Quora page of Jeff Dean facts, including things like compilers don't warn Jeff, Jeff warns compilers. Jeff occasionally compiles his code just to see if there are bugs in the compiler. And my favorite, Jeff Dean doesn't actually exist. He's really an AI that was created by Jeff Dean. So you'll have to excuse me if I ramble because I am starstruck. But thanks so much for taking the time to be on the podcast.
Oh, it's my pleasure.
Why don't we get started by having you tell us a little bit about your background and how you got involved and interested in ML and AI?
Sure. So, I've always been interested in computing, and I moved around a lot as a child. So I went to 11 schools in 12 years.
Oh, my goodness.
Several different continents. I lived in Hawaii, Boston, Uganda, Boston, Arkansas, Hawaii, Minnesota, Somalia, Minnesota, Atlanta, and then back to Minnesota for college. And
was this were you an army brat or something like that?
My dad did tropical disease research and epidemiology.
Okay.
My mom was a medical anthropologist.
Okay.
So, and they like to move. So I moved.
Nice.
And then when I arrived at University of Minnesota as an undergrad, just before doing a senior thesis, I took a course on parallel and distributed computing.
Okay.
And then I worked with the professor who taught me that to do a senior thesis on parallel training of neural nets.
Okay.
Because I sort of, at that time, people were very interested in sort of neural nets as a interesting abstraction for solving problems. And at that time, it seemed like they could do cool things on toy problems, but not much on very large scale problems that people cared about.
Okay.
And I thought maybe if we could get like a 60x speed up on a 64 processor machine, we could do much bigger problems. And so I worked on some algorithms for that. But as it turned out, we needed like 1,000,000 times more compute, not 60x.
So you had to wait that one
And
out.
so I sort of said, filed neural nets away as kind of an interesting thing, but then went off and did a lot of other work. I eventually went on to grad school, did compiler optimization research, then came to Digital Equipment's research labs in Palo Alto and worked on a variety of things, including information retrieval on the web, profiling systems, various things like that. Mm-hmm. And eventually came to Google in 1999 when we were a fairly small company. We were all kind of wedged in a small office on University Avenue above what's now the T-Mobile store. And started working on sort of large-scale distributed systems for sort of core Google products, and sort of worked first on our first advertising system, and then spent many years working on sort of Google's distributed search systems, including the ranking system and also the crawling, indexing, and query serving systems.
Okay. And a ton of other stuff. MapReduce?
Yes. So then kind of towards the end of working on the search system, my colleague Sanjay Gamawat and I and some other people have started working on sort of core infrastructure systems for dealing with large amounts of data. How can you efficiently process large amounts of data on sort of a collection of unreliable computers? Sanjay and I came up with this MapReduce abstraction in the context of sort of rewriting our crawling and indexing system, where you want to go from having a bunch of raw pages on disk that you've crawled to actually having all the data structures built for serving Google queries. And there's a whole bunch of stages there that involve processing the pages and like doing things like extracting all the links from the pages and building a link graph and identifying the language of each page. And conceptually, they're all pretty simple. But when you're trying to deal with making them reliable computations across lots of machines, if you sort of individually conflate the sort of low-level mechanisms for reliability and the high-level thing you're trying to do, which is figure out what language each page is in or extract links, it becomes kind of complicated to do. But if you have this nice abstraction, which MapReduce seemed to provide, you can actually separate those and build an implementation of the MapReduce abstraction that allows you to sort of deal with lots of things in there, like reliability and automatic parallelization across however many machines you want to throw at the problem, dealing with stragglers. So even if a machine doesn't die, it might be running slowly because it's doing other stuff on a shared environment. And then you can express a lot of these fairly simple computations using fairly simple abstractions of MapReduce.
Right. One thing I'm curious about is a little bit of a history of machine learning and AI at Google, right? Leading up to TensorFlow and some of the things you're doing around the TPU. But what's your earliest, exposure? What was your earliest exposure to ML here at Google?
So we've been using collectively machine learning at Google for quite a long time.
And you can argue that the PageRank, the kind of the beginning of Google, is machine learning, right?
Right. So across lots and lots of our products, we use machine learning in various ways. Until maybe about 6 or 7 years ago, typically not deep neural networks, but simpler methods like logistic regression or sometimes simple counting-based statistics methods for estimating probabilities of various things. So we've had a long history of that and built systems around how do we actually scale those kinds of systems to, very large amounts of data. Some of them are embedded in core products that are pretty important. And then about 7 years ago or so, we started to look into how to use deep neural nets and see if we could make those scale to problems we cared about, very large scale problems, because there were signs of various successes in using neural nets for things like speech and vision on a small scale that were starting to appear in the academic literature as sort of the beginning of the revival of neural nets happening in kind of 2007, 2008.
Right.
And so in 2011, we started to really look at this in earnest within Google. Andrew Ng was spending a day a week at Google sort of consulting, and I happened to bump into him in the micro kitchen and said, "Oh, what are you up to?" And he said, "Oh, I'm kind of figuring out what I'm going to work on." But at Stanford, I'm starting to look at how neural nets can solve different kinds of problems, and they're starting to be successful. And I'm like, "Oh, really? I did my undergrad thesis years ago on those." And
oh, wow.
and so we kind of got excited about trying to put together a small effort to scale neural net training to build very big neural nets and see what we could do with them. Simply because, we felt like if they're having success on small scale, then building bigger ones would be even better.
Nice. And did the work on TensorFlow lead or follow directly from that? How did that evolve?
Yeah. So the way this happened was we actually started building a different software system called Disbelief, for distributed belief, and also as a joke because people didn't think this would really work out. So I called it Disbelief. And basically that was a sort of programming abstraction for neural nets that wasn't, in retrospect, it wasn't as flexible as we wanted it to be, but it would allow us to express kind of in the same way that MapReduce was a programming API. This was an API for neural nets. It was sort of layer-based implementations where you'd have a forward method and a backwards method. And so you could compose together layers of neural nets with different kinds of computations in each layer. And it was good for expressing things like convolutional neural nets or LSTMs or feed-forward neural nets, those kinds of things. And we started applying them to computer vision. So we did some work on unsupervised learning with autoencoders for vision problems.
Okay.
We actually didn't have GPUs in our data center at that time. So to get enough computation, we ended up parallelizing these computations across large numbers of CPUs because that's what we had in our data center at that time. And so we trained a neural net with like 2 billion parameters at that time, which was quite a lot, and used kind of 16,000 cores for a week to train a pretty large-scale autoencoder, and found that it could do interesting things like, despite being trained on completely unlabeled data, some of the neurons at the top levels of this large neural net started to be responsive to things that resembled sort of high-level human explainable features, things like, a kind of cat-like face or the back of a person kind of thing. And so it's clearly learning interesting high-level concepts despite not having any labeled data.
So you kind of started with Disbelief. What were the challenges or issues with Disbelief that led you to say we need something new and better?
I mean, I think we realized that this sort of backward computation fit some kinds of expression of machine learning models we wanted to be able to express, but it wasn't as general purpose as we would like. And so we looked at things like Theano, which was a open source package from University of Montreal that had more of a sort of auto-differentiating graph-based interpretation of how to express these computations. And we sort of used that as a rough programming model, but focused on making this sort of a high-performance scalable implementation. And also we wanted to be able to run this in a variety of different environments. So we've always wanted the TensorFlow system to support running machine learning wherever machine learning wants to run, which is a lot of places these days.
Right.
So you want to run it on things like mobile phones. You wanted to run it on a desktop machine with or without a few GPU cards. You want to run in a data center environment where you have lots of machines, each with maybe perhaps several GPU cards. you want to support kind of new and emerging hardware accelerators for machine learning that are appearing both on the data center side in high power environments, but also in sort of things like mobile phones are starting to get kind of these machine learning accelerators. You want to make sure you do take advantage of those as well.
Yeah. On the topic of machine learning accelerators, Google's now on the second version of the TPU. The first version was focused on inference. The second version added, training capability. I'm curious what your general thoughts are on the acceleration space. I mean, you've noted a couple of times now at NIPS and this presentation you were at, I'm sure other places, that when you look into your crystal ball, you see that it's foggy in terms of what we're going to need from accelerators. And so that leads you to some specific, that leads you to think that we should be a little bit more open-ended in terms of where we're going with hardware accelerators. You can do a better job of, clarifying your position on these.
Yeah, so I would say about 4 years ago, we realized that neural nets were going to be a really big sort of feature in lots of our computation at Google. Yeah. And if you look at trying to run all the inference we wanted on the existing data center machines with CPUs in them, that was probably not going to cut it because we wanted to, for example, I did some very rough back of the envelope calculations and said, okay, if every user talks to their phone for 3 minutes a day and we need to do speech recognition on that, then that alone would mean we need to double the number of data centers we had at a very rough level. And that sounded kind of untenable. So we realized that inference was going to be the first important thing to tackle from an acceleration standpoint because any services where you have a growing number of users or a lot of users already, inference is a much bigger cost than training typically. And inference is also a much simpler problem to tackle from an acceleration standpoint because typically you can get a single chip to do inference for a whole model. And then if you need more capacity, you can just stamp out more copies of that chip or more cards that you insert in a machine or a variety or a bunch of machines.
Kind of embarrassingly parallel.
It's embarrassingly parallel. Right. Each chip can handle inference for the model in some modest batch size, and you just kind of go from there. And so the first version of the TPUs that we built was an inference-only accelerator, really. It supports 8-bit quantized integer arithmetic. There's a paper in ISCA, which is a big computer architecture conference that describes that in more detail if readers or listeners are interested in the details. But we tackled that first because that would help us with scaling and using neural nets in many more places in our products. So now whenever you do a query or you're touching inference accelerators in many ways. So for search ranking, for various pieces of other aspects of dealing with forming the search page. For Google Translate, it's used for whenever you speak into your phone, and that's the recognition is done in the data center. There's inference accelerators there helping with that.
Is the implication then that you're using inference accelerators beyond deep neural nets and for traditional machine learning as well?
No, all those are deep neural. Yes. Yes, that's another wave that's been sweeping across many, many Google products and features in Google products and so on, is we're using deep learning. Initially when we started looking at neural nets in our group in 2011, a handful of product groups started looking at, how can we use them? So we worked closely with the speech team, with the image search team, and with Disbelief, our first software system, that made it easier for teams to sort of start training neural nets for their own problems they cared about. And so, eventually 50 teams or 100 teams were using deep neural nets with the first system, Disbelief, that we put together. And like many things, it kind of spreads organically throughout the organization, because as soon as one team uses deep neural nets to solve a problem and another team kind of hears about it and says, hey, that sounds a lot like our problem. I wonder if we could try it for our problem as well. And there's, mailing lists where people can post questions like, hey, I'm having trouble with this, and people will chime in. That's generally the way these kinds of things spread throughout Google. And so we have this kind of nice exponential looking curve of how many different deep learning models are used in production across lots of Google products.
You have a sense for, on a percentage basis, for example, how much of that usage is, what we traditionally associate with deep learning, audio, video, image versus other types of use cases?
Quite a lot of it is in sort of more textual-oriented applications. So things
in fact, including text in that. Yeah, I guess I'm curious more specifically if Google is, in this time working with deep learning, identified and productized, I guess, thinking about mapping, non-traditional deep learning problems to the deep learning domain.
Mm-hmm. I think our experience has been that for problems where you have sufficient data and sufficient computation, you can apply deep learning to a wide variety of problems, both kind of more perceptual kinds of things like speech and vision, but also natural language processing problems, kind of more structured prediction problems. And in general, it doesn't work perfectly on every problem, but the vast majority of problems we try these approaches on tend to work pretty well. Okay. So,
is there ever a problem at Google for which you don't have enough data?
Sure. There are definitely some. Like if you want to predict if a machine is failing, that sometimes you don't have that many examples of failed machines. So that's the kind of thing where you might have less data than other kinds of problems.
Kind of the anomaly-oriented cases.
Yeah. One of the things that is a pretty useful general technique for what you might think of as non-traditional things is to take kind of discrete features. Like maybe you have some model that wants to use the country where a user is located. And you can actually put discrete features into an embedding space. So similar to like the word2vec model where you have discrete words and then you represent each one of those words by say 100-dimensional or 1,000-dimensional vector. And through the optimization process, you kind of nudge these vectors around in this super high-dimensional space so that similar things are kind of nearer each other in this high-dimensional space. You can actually do that with more discrete things like the country where a user is located or whether they're on what kind of model phone they're on. Because maybe some phones have very big screens and people behave differently in how they use those than other kinds of phones. And so you can put an embedding vector on the model of phone and then kind of nudge the point in this high-dimensional phone or device space nearer to ones that seem to behave similarly and other ones maybe form other kinds of clusters in this high-dimensional space. And that's a pretty common technique we use across lots of different problems here that is not really a research thing. It's kind of a more of a practitioner. Like if I'm trying to solve this kind of problem with a bunch of discrete features, that's something you might try using, but it's not like there's really a good single paper you go to discuss this, except word2vec kind of is, or things like that is representative of that, but it's not necessarily obvious that you can do this for non-words and non-language things, but for all kinds of things. If you had videos you're trying to recommend in some high-dimensional space, you can represent each video as a high-dimensional vector.
Right. So we were talking about the TPU and hardware acceleration generally. Do you have a sense for, when you did your back of the envelope calculation, did you project out, some number of years and kind of get a sense for the percent of, total compute at Google that will be dedicated to inference? Do you have a feeling for that?
I don't have a super great feeling because we're still discovering. Training is certainly a big deal as well. So our first generation TPU was for inference because that's was a more pressing need in 2013, 2014.
Right. But
also it's a simpler problem. You design a chip on a board and that's pretty much the extent of it. For training, that's a much sort of broader scale problem at a systems level, because you need to design both accelerator chips, but also a much bigger scale system that connects those chips together. Because unlike inference, it doesn't sort of scale just embarrassingly parallel where you just plunk in a bunch more cards. You actually need more compute than you can fit in a single chip for large scale training problems. And then you need, therefore, to take a much more holistic systems view. How are we going to build sort of a much larger scale system that connects together a bunch of these chips with very high speed interconnects? How can I, have a software story that's easy to take a computation I care about and map it onto, say, a system with 64 or 256 chips, and have that be sort of easy to use for machine learning researchers and practitioners without sort of getting into the guts of, them worrying too much about how to parallelize things across these different devices. And so it's just a much bigger scale problem. And so the second generation that we tackled was a system for both training and inference, and was much more holistic than a single chip. It's like these large scale TPU devices, which are 4 chips on a board. And then those are designed to be connected together into much larger configurations of 64 devices, 256 chips. There's a custom 16 by 16 mesh network that, or toroidal mesh actually, with wraparound links on either end.
On the device or the broader system?
On the whole broader system.
Level?
So the whole system is like 4 racks in size. Looks really like a machine learning supercomputer. And those are the kinds of things that we're now applying to much larger scale problems. And the reason we're doing that is because we see continuing gains as you're able to tackle larger and larger problems. So, for example, the deep learning work that we rolled out to sort of completely replace the old style phrase-based translation system in Google Translate with a neural net, is impactful in many ways. So one is that system had been around for a decade. I actually helped do some of the early low-level software for some parts of that system. And it was a very complicated system in software terms. It had like 5 or 6 different sort of distributed systems in it. And then a bunch, there's like a target language model that is spread across 100 machines, where you do lookups of how often a bunch of 5-word phrases occur. And that language model can tell you how often every 5-word phrase in English occurs. There's an alignment model for how words in English and French align. And then there's like phrase tables and dictionaries, and then 500,000 lines of code to glue all this together. So the new system is literally a TensorFlow model with a neural machine translation model that we've published a paper about, and is like 500 lines of TensorFlow.
Wow. And
just learns from lots and lots of data. And not only is the system much simpler, but the translation quality is much, much higher. The gains we saw from moving from the old system to this new system were equivalent or larger than the gains in quality improvements in the previous decade of working on improving the older system. And so that's just a sign of something can be dramatically simpler. And because it's learning from lots of observations, it can actually do a better job of the task you care about. And the way this gets back to TPUs is, for some of the language pairs that we rolled this out on, we actually have a lot of data, and we could only train on 1/6 of the data we have. So we could only get through 1/6 of the data once in the sort of time budget we'd set for each language pair. And that system supports, roughly 100 to 100 other languages. So there's like 10,000 language pairs you need to support.
And so that's now on TPU2, or was that before?
That's now training on TPUs, and it's actually running inference on TPU v1. So, but before we had TPU v2 rolled out, it was training on lots of GPU cards.
Do you see the TPU effort broadly kind of replacing GPUs at Google and kind of decoupling Google from a dependency on GPU suppliers?
I wouldn't frame it quite like that. I would say, because we're designing both the TPU and we have a lot of machine learning researchers and also are building software to map these sort of style models onto the TPU, we can have sort of much tighter feedback loops in sort of doing vertically integrated decision making for what the future of TPUs should look like. But there's some things that TPUs don't necessarily do well that GPUs do extremely well. But the kinds of things that do run on TPUs, we think are pretty interesting and compelling from a performance standpoint. One of the things we really crave is to make turnaround time for machine learning research experiments much faster. And so, there's a qualitative difference as a researcher if your fundamental experimental turnaround time is measured in, an hour rather than a week.
Right.
It just feels very different. You can be much more productive. You can try more things out. It's not a big, effort where you start up an experiment and then you've forgotten what you've actually started by the time it finishes in a week. Instead, you try many more things. And so getting that time down just improves the productivity and the rate at which we can try out new ideas, which is really super important in this kind of new and emerging space.
And is that an exercise in driving up teraflops as quickly as possible, or is it more nuanced than that?
So it's a few things, right? One is obviously you want more raw teraflops, but also you want software layers that make it easy to use those teraflops, right? You don't want to have to write complicated code in order to have a research idea you just thought of be mapped onto those teraflops.
Right.
So if you can make software tools that make it easy to express ideas that then can take advantage of, say, a whole TPU pod relatively quickly, that's just generally going to be better. And so it's really requires work at all these different levels of the sort of hardware design stack, the software stack, the ease of expression for different kinds of APIs that you might imagine using for expressing machine learning computations.
Are there a set of things that, a set of tooling that Googlers take advantage, or that Googlers kind of take for granted that that you think that need to evolve, I guess, more broadly and be, someone needs to provide in order for, folks to take advantage of deep learning and be able to iterate as quickly as Google does?
Well, I think one of the things that we're trying to do is to, and part of the reason we decided we would open source TensorFlow, and so we open sourced TensorFlow at the end of 2015, was we wanted the tools that we use to also be sort of more broadly available to the community, and then have the community collectively work with us to improve those tools. And I think that has actually played out reasonably well. We now have tons and tons of people using TensorFlow. We have, obviously a smaller set of people working to improve the core set of TensorFlow APIs and algorithms and implementations, but lots of contributions from across lots of other big companies, lots of smaller companies, people working on their own as hobbyists, really are working collectively to improve those tools. And I think that's really good because it gives you a common language for expressing machine learning computations that is really useful to have ideas spread more rapidly through a community than they would if you relied on just publishing a paper and describing something. And when you do that, you by necessity leave out a lot of details, right? English is kind of a poor way of specifying exactly what to do. And so by allowing people to share sort of working implementations or open source models that they care about, I think you can get that spread that was happening already within Google of one team picking up what another team has done and trying it on their problem.
I guess I'm curious about so look, TensorFlow, today is, in some ways, look at the way Google was thinking about this 5 years ago and what was missing 5 years ago, right? If you look at, the way Google's thinking about it today but we'll be still missing for the industry in 5 years. What's the kind of the future of that software stack? This is kind of a clumsy way of asking the question, but, Google had Borg, and then that turned into Kubernetes. There was Disbelief, which, became kind of publicized as TensorFlow or evolved into TensorFlow in some ways. I'm imagining there's actually in the conversation with Ryan Poplin, we talked about a lot of the data augmentation pipeline that, as a researcher, he just takes for granted. It's just there. I can imagine that being publicized or turned into open source code by Google or, someone else. And I'm just wondering if we can kind of tap into your today as a crystal ball for, what some of the gaps are in the software pipeline that need to be figured out over the next few years to really make deep learning allow folks to iterate more quickly.
Right. So, I think one of the things that's happening is people are open sourcing a wide variety of different tools built on top of TensorFlow or that sort of run in phases, and then you sort of run TensorFlow as sort of the core computation engine. And I think that's really powerful. And most of them are sort of particular things rather than a general framework that makes something different.
Yeah.
But they all add together because now there's this really large community of different pieces and building blocks that you can choose from when you're solving new problems. One of the things I'm pretty excited about in terms of the research our group is doing is this notion of automating machine learning, right? I think even today with the explosion of interest in machine learning and more people are entering the field, there's still an incredible shortage of people who actually know how to take data and computation and have the expertise to then make a solution to a machine learning problem.
Yeah.
The way I like to phrase this is there's, maybe 10,000 organizations in the world who are actually really practically applying machine learning in a production way to their problems and their settings and have hired people with strong machine learning expertise. But there's probably 10 million organizations in the world that have data in electronic form that could be used for machine learning and have problems that would be amenable to machine learning. One example is every city in the world should be setting their stoplight timing by machine learning, right? Like right now, they probably have two lookup tables. They have rush hour and not rush hour.
Right.
And you select among them via the time of day.
Yeah.
But you can imagine with a computer vision-based stoplight, you could just figure out, are there cars coming in which direction? And if not, turn the light appropriately and maximize throughput of cars through an intersection or through the collective set of intersections in a city. That's not something most cities are probably doing today. Some are, but most of them are probably not. And so I think the idea behind AutoML or meta learning is that you want to be able to solve new machine learning problems automatically without a human machine learning expert sitting down and saying, okay, I'm going to solve that in this particular way. And I think that's going to be a really promising and fruitful way to get more machine learning used in the world to solve problems that are important.
What do you project the timeline, or how do you see AutoML evolving over time?
Yeah, so we're continuing to push on the research aspect of it. It's obviously an ambitious problem to be able to take any problem and solve it automatically. I would say what we have now is we can now solve problems in a set of restricted domains automatically and be able to take a new problem and automatically solve it in one of those domains.
Can you give me an example of that?
So we actually have a launched product that we've jointly worked on with our cloud organization,
Cloud AutoML,
that initially can solve computer vision problems. And there's tons and tons of organizations that fall into the category I was saying, where they have a bunch of images of things they care about. The sort of default ImageNet model isn't exactly right for their problem.
Okay.
Like they want to be able to identify, is this a broken airplane part on their assembly line or a not broken one? So they have a bunch of images of that, some of which are labeled as, broken propeller, and some of which are labeled as, not broken flange or something. And so you can take those image data sets and now automatically solve classification problems to high level of accuracy, much more than you can get just by doing transfer learning from, say, an ImageNet model that you've already trained. And that's already going to be useful for a pretty wide variety of companies and organizations. And broadening out the set of domains in which that approach works is something we're actively working on. You'd like to do this for language problems, for recommendation problems, speech problems, a wide variety of these things.
Do you have a kind of a research taxonomy of AutoML? There's the neural architecture search. There's kind of meta learning stuff. How do you think about the different pieces and the way they fit together?
Yeah, I think we started this investigation in our group with the neural architecture search work. We've also been working on evolutionary approaches for those same kinds of problems, just as a way of comparing several different approaches for tackling the same problem. I think that's often useful to ground work. Is what you're doing the right direction by trying out several approaches. There's a bunch of other work we've been doing on learning things that are not just the architecture, but things like learning new optimization update rules. Traditionally you have SGD, which is a very simple update rule. You take the learning rate times the gradient and you add that to the parameters. And then there's things like SGD with momentum and Atom and Attograd that have been developed by humans and seem to be effective for a variety of problems. We actually published a paper in our group on trying to learn optimization update rules, symbolic optimization update rules, and just gave it kind of the raw primitive things like the things that occur in the expressions for SGD and SGD with momentum and a bunch of other kinds of symbolic updates. And then it learned to stitch them together. And it found sort of 15 different optimization update rules that are all better than all four of those sort of things.
Interesting.
Which is pretty interesting. And some of them had sort of common characteristics that you can kind of get insight from. So that's kind of
And how did you represent that problem so that you could do it in a symbolic domain?
Oh, so you just it's sort of similar to neural architecture search, except what you're spitting out is not an architecture, but a symbolic update expression for optimization.
Okay.
And so you give it a bunch of primitives and say, please spit me out a symbolic update rule that has, no more than a depth of 3 in a symbolic expression tree or something. And then you can search over plausible symbolic update rules, including things like, you accumulate the running average of the gradients, or you multiply by the learning rate, or you divide by the recent parameter updates or something.
Interesting.
And so one thing it found was an interesting rule of, I'm trying to remember the exact rule. It's like e to the sine of the current gradient times the sine of the recent running average of gradients. And so if those are the same, it's going to scale things by that. And if they're different, then it's going to slow way down.
So this thing basically just spits out your next 15 papers or something like that, right?
Something like that. Although probably you'd take the best one and do that. But, it is interesting that the kinds of things that are, if you have a problem that is automatable in this sort of searchable way where you have a clear reward function and some space to search over, I think this is more general than just how do you find machine learning sort of ideas, but scientific ideas more generally. If you can automate that process, because what a scientist does is they run a bunch of experiments and then they look at the results of those experiments and then they figure out what are the next experiments to run, right? And so integrating the results of the previous experiment back into deciding what the next things are to run is generally a pretty slow process if there's a human in that interpretation loop. And so you can actually get a lot of benefit for real world problems if you have sort of a clear reward signal by essentially using reinforcement learning or perhaps evolutionary search to optimize that reward.
Are you doing much with program learning? Have you published on program learning?
We do have I mean, you can think of neural architecture search as a very restricted form of program learning.
And the optimization stuff you described as well.
And the optimization stuff. We're also doing some more traditional symbolic computer programming language synthesis work. We've published a little bit of that, but not. It's sort of an early emerging research area for us. We're pretty excited about it because we think it's got a lot of potential benefit to sort of provide tools for programmers to sort of take some of the work that is traditionally done by programmers that could be done in a more automated way, and allow programmers to spend more of their time on the things that are sort of higher level, more difficult to do, and take away some of the drudgery work that programmers currently sometimes do. So,
yeah, where do you think, how would you characterize, where we are and how that work evolves over time?
Yeah, I mean, I would say we're pretty early in that work really having real world impact, but I think it's definitely an interesting direction, because obviously if you can look at a problem and come up with an algorithmic expression of how to solve that problem, that's a pretty important and impactful thing, but we're very far from being able to do that in general.
Yeah. Maybe circling back to TPUs, what can you say about TPU v3? Like what needs to be, where does the work need to continue there, and what do you expect that the future holds in that direction?
Right. I mean, I think one of the things about machine learning accelerator hardware is it's hard to really read the future out far enough in this very fast moving field. If you look at to give an indication of how fast this field is moving, there's this great exponential growth chart of the number of machine learning papers on archive since 2009 or 10 or something. It's gone from like 1,000 per year up to 20,000 papers per year. Right. So that's like almost 100 papers per day being published in the machine learning field on archive, which is sort of crazy, right? It's like an entire conference every day. Obviously they're not all peer reviewed and so on, but it's a very fast moving field with lots of people with different kinds of ideas and backgrounds coming into the field and bringing their perspective on how to solve problems there. And
have you developed yet the deep neural net to summarize all those papers off of archive so that a researcher could actually keep up?
We are working on summarization, but sadly it is not yet at the level where we can understand all the archive papers published today and tell you which ones to look at, but that would be cool. But I think that's an example of, if you're starting to design a chip or a system for doing machine learning acceleration, currently what we've focused on is trying to make low precision linear algebra super fast, right? Because that seems to be a basic building block that applies to nearly all the deep learning sort of algorithms and systems we've looked at. There's a bunch of kind of interesting exploratory work in very low precision kinds of work that have been sort of proven out on small scale problems in software simulation to show that in some cases you can make 4-bit weights and 4-bit activations work. And obviously, if that worked in general across all problems you cared about, that would be pretty cool. And you might really sort of bet on that in your accelerator hardware. I think the state of this is such that it's been shown to work on some kinds of problems on modest data set sizes. So more experience is needed before you really bet on putting it in as the only thing in your accelerator, right? Because your accelerator, if you design it today, sort of pops out of the fab and into your data centers a year and a half or 2 years from now, and then it has to live for 3 years. So you're sort of wanting to bet on things that you're pretty comfortable are going to be important things for the 2 to 5 year time frame from now. And so that means you can have some experimental things in there, but not sort of the whole chip being experimental. Although I will say there's a bunch of startups now in this space that are, essentially being funded by the VC community to try out ideas. And I think that's actually kind of cool because there's a lot of ideas being tried out in the startup space, some of which are likely not to be the best ideas, but the experiments are being run. And some of which may turn out to be influential and interesting and exciting and inform what we should do in terms of building sort of next generations of ML accelerators.
Yeah, I've kind of posited that in a world where deep learning, machine learning, enterprise general workloads are kind of shifting to the cloud over time, and all of the cloud vendors are investing heavily in their own hardware to accelerate their workloads. In part, I propose or suppose to kind of make sure they're not dependent on any particular accelerator vendor in their supply chain. I kind of wonder what the future holds for these startups that are kind of going off on their own and building out these new accelerators. Like, who are their customers going to be?
Mm-hmm.
What's your take on that market and kind of how it shakes out?
Well, I think it's hard to say, and I'm not in the business of picking winners in the chip startup space, which is fairly good. But I think obviously some of them might get acquired. Some of them will sell equipment to cloud providers, probably cloud providers, or to people who want on-premise machine learning and not running their compute in the cloud. Mm-hmm. So I think there's definitely avenues for them to be successful. And, it's just a little unclear exactly which of the ideas that are being tried out will be sort of good in terms of, providing really high performance for general things, or maybe there's some restricted set of models where one particular hardware vendor's thing is super fast, but it doesn't really run other things very fast. Mm-hmm. I do think part of this is driven by the fact that Moore's law speeding up general compute has basically dramatically flattened off in the last 6 or 7 years. Mm-hmm. And so now we're at the point where a lot of the innovation is going to be on the computer architecture side rather than just relying on the fab people to give us like smaller features and faster transistors every 2 years like they had been. And so that will mean there's now this really wide open space. And the other thing is that now that we know machine learning computations, deep learning models in particular, are so applicable to so many problems that previously, when you were building like specialized hardware for a particular thing, it would apply to a relatively modest part of all the computing you want to do. Right. You might speed up a compression algorithm by having custom compression circuits or something. Mm-hmm. But that's not actually that much of what you want to do generally.
Right.
But now you have machine learning computations where it seems plausible that might be a lot of what we actually want to run on computers, say 5 years, 10 years from now. And so you can now build specialized hardware that doesn't just apply to like a little bit of your computation. It applies to everything, a lot of it. And so that I think is pretty exciting because now general purpose accelerators apply to such a wide variety of things we care about. Speech, vision, language, all the things you can imagine computers really wanting to do. Most of them you can imagine machine learning tackling, and you can imagine machine learning acceleration hardware being an important part of how you make that scale and be fast.
Mm-hmm. So your counterpoint is then that it's just that the market is going to be so massive, or is so massive, that there's potential opportunity for different approaches.
I think so. And I think I would liken it to this, like a big Cambrian explosion of computer architecture again. And now lots of ideas are being tried out, and it's unclear which ones will sort of survive this Cambrian explosion, but many of them probably will, and that'll be kind of cool, exciting.
Awesome. So to wrap up, I'm wondering if there are 1, 2, 3 things that are core to the Google way of thinking about deep learning, machine learning, AI, or even the Jeff Dean way of thinking about machine learning and AI that a lot of people don't know, but they should. Even better if they're not things that you talk about all the time. Like, what are those kind of hard fought, lessons that, folks need to know?
I mean, I think one of the things that has struck me a little is I was preparing to give a talk at the National Academy of Engineering last summer. And turns out the National Academy of Engineering put out a list of 14 sort of grand challenges, engineering challenges for the 21st century. And it's a pretty good list. It's like, make solar energy efficient and affordable, advance health informatics, bunch of things like that. And I was struck by how many of those things seem amenable to machine learning being either key to solving or an important part of solving some of these problems. Even things that seem kind of somewhat a field, like more like chemical understanding or better chemistry. I think actually machine learning in the last few years has shown that it can actually be applicable to a lot of scientific problems, including better modeling of chemical dynamics and these kinds of things, and more rapid evaluation of materials and things like that. Yeah. So, and we've been doing a lot of work on healthcare related problems using machine learning. And I think I'm struck by the fact that a lot of these sort of core machine learning algorithms are going to have impact not just in kind of computer science and machine learning, but because they're applicable to so many things across, a really broad set of problems in society. Things like healthcare, self-driving cars, obviously, material design. All these things I think are pretty impacted by better machine learning and better machine learning hardware and advances in this field. That's pretty cool. That's why so many people in the world are interested in this field, because I think it's going to do amazing things for the world.
Awesome. Well, Jeff, thank you so much.
Cool. Thank you.
All right, everyone, that's our show for today. For more information on Jeff or any of the topics covered in this episode, you'll find the show notes at twimlai.com/talk/124. As you know, we love to receive your questions and feedback about the show, so don't hesitate to comment there. Thanks so much for listening, and catch you next time.